So now I'm going to quickly hand over to Einar. Can Haifa make Einar a host, please, so he can share his screen?
He is
great. Okay, so I'm now going to hand over to or welcome Einar Steingrimsson from the University of Strathclyde, and he's going to tell us about permutation statistics, patterns, and moment sequences. So over to you, Einar.
Thank you, and thanks for inviting me to give this talk. I should tell you that the internet connection I was told would be working where I am now isn't working as well as it should, so I'm connecting via my phone just in case something happens and I lose the connection. You know what's going on. So let me share the screen and let's see. Does this work? Because I don't see it myself.
That looks good, but you're not in presentation. Oh yeah, you're in presentation mode for the PDF. That's perfect.
Okay, so let's get started. I need to keep track of the time, of course, also. So this is about combinatorial sequences that are moment sequences of probability measures. And here is one example: the number of perfect matching, which is counted by the double factorial of 2n minus 1, this number is the these are the moments of this measure, e to the minus x squared over 2 and divided by 2 pi. And an equivalent statement, which is maybe more amenable to the sequence that we're looking at, is that the so-called Hankel determinants of the sequence in question are all positive, and the first one has to be 1. So a Hankel determinant is a determinant of a matrix that is formed by taking there are matrices, square matrices of sizes 1, 2, 3, etc., 1 for each n. And the nth matrix has as its first row the first n letters in the sequence, the first n numbers in the sequence. The next row is shifted by 1, and so on. So that's what we're trying to find. We want to know what conditions on combinatorial structures would guarantee that you have a moment sequence in the counting sequence. So here is some data. Andrew L.V. Price looked at all the sequences in the online encyclopedia in June and found out that 4.7% of them roughly could be moment sequences. They passed this test for the Hankel determinants. And so this is the question we want to try to answer, and I'll tell you a few things that we know and some things that we conjecture. So here are two combinatorial sequences: trees on labeled nodes, which are known to be counted by n to the n minus 2, and then trees on unlabeled nodes. The first of these is a moment sequence, and the second one isn't. Here is another example. So if we look at the consecutive pattern 132, that is permutations avoiding this, meaning there are no 3 consecutive letters in the permutation that are in increasing order, then we get the sequence 1, 1, 2, 5, 17, etc. And for permutations avoiding the consecutive pattern 1, 3, 2, which means no 3 letters in the permutation appear in this order, where the first one is the smallest, the next one is the biggest of the 3, and the last one is in between. So these two sequences count very similar things. One of them is a moment sequence, the other isn't. And so the question is, can we find any structural properties of our combinatorial object that determine positivity? And I will not have any good answers to that, but I'll show you lots of examples. So here's a Motzkin path, which I assume most combinatorialists know by now. And this continued fraction is a generating function for the Motzkin paths. And as it happens, the level steps, so a Motzkin path is a sequence of up, down, and level steps. And the level steps correspond to the red z that in what we could call the denominators here, and the black z squared correspond to pairs of up and down steps. Okay. Now, we can put weights on Motzkin paths, and if we do this kind of weighting, where an up step at height 2 can have 2 different labels, and likewise for the corresponding down step, and a level step. So if we're at if we have an up step at height k, then we have k different labels that we can put on it. A level step at height k can have 2k plus 1 different labels associated to it. If we look at all the Motzkin paths that are weighted in this way, then we get this corresponding continued fraction. And this, if we turn this into an ordinary generating function, the coefficients are n factorial. And this is a special case of a very general correspondence by Philippe Flacheolet from 1980. So we have a continued fraction that we use to record lots of statistics on permutations. And this looks like a horrible mess. It's 14 different parameters. And I'm going to show you a little bit about what these parameters are used to count. And here, this bracket here, bracket n, is just the usual PQ bracket that I hope everybody knows. And the plan is to find a bijection that takes permutations carrying lots of statistics to Motzkin paths corresponding to this particular continued fraction using Flacheolet's correspondence. And again, this is a lot of stuff here. We have these 14 different indeterminates that in this continued fraction, and we have Motzkin paths that are labeled by the same parameters, and they're labeled in this way that I'm showing here, but I don't want to go through all the gory details. I'll tell you something about what this counts. And this is how the parameters get attached to the indeterminate z and z squared in the continued fraction. So this is the general term of this continued fraction. And here, on the other hand, we look at permutations, and we have 14 statistics defined on permutations. And all of these statistics are based on exceedances, or exceedances and inversions. Now, so here we have the 2-line notation of the permutation. And so in this picture, we have an arrow going from 1 to 5, because in the first place in this permutation, we have 5, and 2 goes to 9. So there's an arrow from 2 to 9. These are both exceedances because the letters here are bigger than the places they sit in. And the exceedances are red. Anti-exceedances are blue arrows going down to the left. And they are letters that are strictly smaller than the places they sit in. And then we have one fixed point here. So I'm showing one of the inversions in this permutation, the inversion between 5 and 1, the letters 5 and 1, that is the inversion between letters in places 1 and 4. And of course, in this picture, every inversion is a crossing. But we need to refine these. And here, for example, 7 is a linked exceedance. And that's because the letter 7 is in a place that is smaller than it is. So 7 is you could say the top of an exceedance, but 7 is also the bottom of an exceedance, because in place 7 we have a letter that is bigger than 7. So that's indicated by this dotted line that connects to exceedances. So this exceedance is linked, and there are linked anti-exceedances. Anti-exceedances defined in an analogous way, and there's just one of these here between the 4 is a linked exceedance, anti-exceedance. And the inversion between the letters 9 and 6, well, that's an inversion between an exceedance and a fixed point. We need to keep track of certain inversions, some of the inversions, depending on the character of the letters that are involved in the inversion. So here are the gory details of the permutation statistics. There are 14 of them. I'm not going to walk you through all of this, of course. I'm just going to show you 2 of them. Anti-exceedances are defined by this single inequality, sigma of I, that is the value of the permutation that I is smaller than the place. This is just one inequality. And on the other hand, some of these inversions, or in this case, a non-inversion, is defined in terms of 4 different inequalities. But I want to emphasize that all of our statistics are refinements of exceedances or anti-exceedances for fixed points and inversions or non-inversions. Okay, so we have a bijection, and as is the case with many bijections between permutations and weighted Motzkin paths, once you know what you want to prove, once you've constructed the permutations and with the right statistics corresponding to the Motzkin paths you want to biject to, it's usually fairly straightforward to see to actually write the proof. But I'm not going to go through the proof in detail. Okay, so we have this bijection, and there are several related bijections in earlier literature. The one by François and Viennot is the first, and that was actually the one that inspired Flageolet to generalize this to connections between Motzkin paths and continued fractions. Now, our results generalize most of these bijections in these papers above, but in some cases there's a translation that you have to translate between the statistics that people use, because there are different kinds of statistics used here. Some are based on exceedances like we do, others are based on descents in permutations, and so there is a translation that needs to be done. But what I'm saying is that there is a lot of equivalence between all of these bijections. And then at the same time as Natasha Blitvich and I were writing our paper, Sokol and Zhang did more or less the same thing, except they have an additional 4 statistics. And some of these were originally defined by Sylvie Cortel in 2007 or so. Now, I'm not going to tell you more about the details of that paper, but that's a very nice paper. It's a big paper, but it has lots of nice permutation statistics, and also on perfect matchings and set partitions. Okay, now the number sequences arising from this continued fraction enumerate lots of different combinatorial structures and refined statistics on them. And all those examples, all the meaningful examples we've come up with, are moment sequences. Now, here are some examples. And so on the first row, we have Motzkin paths with a kind of labeling that I told you about initially. You just get n factorial all the permutations. And the corresponding measure is e to the minus x. And so this is just exponential distribution. On the next line, we have perfect matchings with a normal distribution. On the third line, we have set partitions where the corresponding distribution is Poisson. And finally, the Catalan numbers whose distribution is a semicircle. So again, the question is, which of these structures give something probabilistically meaningful? Now, here is this continued fraction, and I'm turning it into a ordinary generating function. So the coefficient to z to the n now is mn. And with very mild conditions on the parameters of this continued fraction, we get moment sequences for these coefficients. And when I say mild, I would say that any settings of the parameters that a combinatorialist would even dream of using, you're going to get moment sequences. So here's the general term in this continued fraction again. And if we set s equal to 0, s is here somewhere. If we set that equal to 0 and everything else to 1, we get a generating function for the number of avoiders of the consecutive pattern 3 to 1. So this counts the permutations of length n where no 3 adjacent letters are in decreasing order. So Here is an occurrence of this pattern because these three letters are in decreasing order and they're all adjacent. This is an occurrence of the classical pattern 3 to 1, but it's not an occurrence of the consecutive pattern because the 5 and the 4 are not adjacent. So this is a result that was first shown by Elizalde, who was using a different continued fraction that he then specialized. When we specialize our continued fraction, we get the same result. And here's that same example again. And here's another example when we set these 5 parameters equal to 0, everything else to 1. We count the number of avoiders of the vincular pattern 2-31 and an occurrence of the vincular pattern 2-31. As here, for example, is an occurrence of the classical pattern 2-3-1, where the last 2 letters in the occurrence are adjacent. So this is an occurrence of the classical pattern 2-3-1, but not of the vincular pattern 2-3-1 because the last 2 letters are not adjacent. Okay, so this was first shown by Claesson and Mansour in 2002. They also started with a different continued fraction and then specialized it to get this. There are 2 more cases of patterns of length 3. If we look at all possible patterns, all vincular patterns, that is consecutive, vincular, and classical, and it's the classical 1, 2, 3, which is counted by the Catalan numbers, as all the classical 3 patterns, and the Bell numbers, which count permutations avoiding 1-2, 3. These are both moment sequences. Of all the patterns of length 3, there's only one that is one equivalence class that doesn't give a moment sequence, and that's the consecutive pattern 1, 3, 2. This also happens to be the only 3 pattern whose avoidance cannot be captured in this continued fraction, because if you try to fit the parameters of this continued fraction to that sequence, you end up with a contradiction. So this continued fraction characterizes patterns of length 3 according to whether they are moment sequences. Now, for classical patterns of length 4, 2 are known to be moment sequences. That is, there are just 3 different sequences, 3 Wilf classes for classical patterns of length 4. 2 are known to be moment sequences, and L.V. Price conjectured in his thesis that the same is true of the third, the 1, 3, 2, 4, which we don't know the enumeration for even. Now, and then Clisby, Conway, Goodman, and Inoue conjecture that the same is true for all 16 Wilf classes of length 5, that is, all counting sequences of permutations avoiding patterns of length 5, and they prove this in one case. We conjecture that this applies to any single classical pattern, that if you take the counting sequence, the number of permutations avoiding any classical pattern, that's a moment sequence. And now I'm going to tell you about something different. So here's an occurrence of the consecutive pattern is 4 letters that and so I'm marking that here. The middle 4 letters 2, 6, 3, 7 also form the pattern 1, 3, 2, 4, and so do also the last 4 letters. So this permutation has occurrences of this pattern starting at all odd locations, and we also say that it is covered by 1, 3, 2, 4 with overlap 2, because the occurrences overlap in 2 places, as you see. And in this particular case, the counting sequence is the Catalan numbers, which is known to be a moment sequence. And for patterns of different lengths and different overlaps, of course, we get many, many different counting sequences. And the number of permutations covered in this way with a given pattern with a fixed size overlaps, this depends only on the first M and the last M letters in the pattern. That's fairly easy to see, where M is the size of the overlap. And here are some examples of nice enumeration sequences, which very few of them are. So if we have a pattern that begins with 1, pattern of length k, begins with 1, ends with k minus 1, then this is the counting sequence. So it's a staggered factorial. If j is 2, then this would be the double factorial. If j is 1, this is ordinary factorial. And if you start with 1 and end with 2, then you get this reasonably nice ratio, which happens to be count also the partitions of set partitions of size kn into blocks of sizes k. And these both of these are special cases of this general case, where if you have a pattern of length k that starts with 1 and ends with k minus d, then you have this nice product formula. In these first three cases, I'm always talking about overlap 1. This last example is for overlap 2. You have a pattern length k that starts with 2k, ends with 1, 3. Then you still have a fairly nice formula for these. But in most cases, the formulas are not this nice. So here is the sequence for the numbers of permutations covered by 2, 1, 4, 3 with overlap 1. And there's no simple expression for this. At least we have not found it. We're pretty certain that that there isn't a simple expression, but we have a general recursive formula. And again, this looks like quite a mess. I mean, there are lots of details to take care of here. And what I'm looking at is a pattern of length k. And I need to look, and I'm assuming the overlap is m has length m. So I need to look at the prefix of length m and the suffix of length m of this pattern, because that's where the overlap happens. And here's the recursive formula. And I'm just going to tell you the idea. First of all, I wanted to tell you that this requirement that I have in the statement that the prefix and the suffix are each increasing is unnecessary, but the proof is much easier if you do that. And then there's a lemma that says you can get rid of that condition. So I'll tell you the idea of the proof, because it's not very complicated, even though the writing down these details is pretty messy, as you see. And the idea is this: we want to find a recursive way of counting permutations covered by this pattern with overlap m. And so what we do is we look at in how many ways we can construct a permutation ending in a particular suffix l, and look at all the possible prefixes L prime of the last occurrence of the pattern in a permutation. And so we are looking at, so we're restricting both of these, looking at each possible case where we have a certain suffix L and a certain prefix L prime in the last occurrence of the pattern in the permutation. And then we just need to figure out how we can pick the letters that lie between L prime and L in this last occurrence. And that's taken care of by this product here. Now, once we have a formula for that, we just refer to induction and jump down to the next length, which is when we remove the last occurrence of the pattern, except for the suffix of length m. So this is a general recursive formula, and we conjecture that for any pattern and any size overlap, the counting sequence is a moment sequence. So we've verified this for all patterns of length up to 20 with overlap 1, and the enumerating sequence is going up to length 50, which means that the Hankel determinants we need to look at to verify this are of matrices of size 25 by 25. For patterns of length up to 9, overlap 2, we can do this for sequences of length 20, and we've done several cases for overlap 3. And in every case, these turn out to be moment sequences. And here's a bolder conjecture, namely that we don't need to have regular overlaps, but that we could have periodic overlaps. That is, The first two occurrences could overlap by 2, the second and third by 3, third and fourth by 1, and then you repeat this pattern 2, 3, 1, 2, 3, 1. Oops, sorry. And we have confirmed this for a variety of examples, but certainly nothing exhaustive to any degree. But there is an obvious, even more general question. There may be no reason to think that periodic overlaps or regular overlaps are any different from just any arbitrary sequence of overlaps. So that's I'm not conjecturing that, but that's what I would like to be the case, and that's what I hope we will eventually be able to prove. So that's all I have to tell you. And if you want to look at these two papers, one of them is published, the other one is in preparation and will hopefully appear in the next couple of months.
Okay, thank you, Einar. Mark had to left, so I will be moderating for the rest of the conference. Any questions from the participants?
Yeah, I know. How do you prove that something is not a moment sequence?
So in most of the cases that we have done that, we just take the sequence and we look at the Hankel determinants. And for example, this pattern that failed, this consecutive pattern, the avoiders of consecutive pattern 1, 3, 2, there the Hankel determinant becomes negative for 6 by 6 matrices.
Ah, interesting. So whenever something is not, it's not a moment sequence, can you easily find it very soon, or sometimes you have to work harder to prove that something is not?
So I mean, all the examples we have found by looking at Hankel determinants for matrices that aren't very big. I mean, we've gone up to 25 by 25 matrices, but it's hard to say. I mean, so sometimes we've never seen any really bad examples where things are fine for the first 20 numbers and then it fails, or for first 20 matrices. So it usually happens faster than that, but we can't know.
So for example, for the famous 1, 3, 2, 4, how far did you go?
So Tony Gutmann and his co-authors came up with an algorithm a few years ago that allows them to count the avoiders of 1, 3, 2, 4 up to length 50. And that gives a 25 by 25 matrix. And so all of these, so the first 25 Hankel determinants there are positive.
Oh, interesting. Thank you.
Thank you. Any further questions, please? Okay, I think we don't have any more questions. Thank you, Einar, for this very interesting talk.
Thank you very much.